Hello everyone, my name is Jesus Torresillas, and today I'm going to be presenting our RAL paper titled Deep-PANTHER Learning-Based Perception-Aware Trajectory Planner in Dynamic Environments. This is a joint work done by myself and Professor Jonathan Howe at MIT. In this work, we look at the problem of how a UAV can avoid unknown dynamic obstacles. That means that the UAV needs to leverage the planned trajectory to make it easier to detect these obstacles. This is something that we solved in our previous work, Panther, but the problem is that the trajectories generated, the solutions, were a little bit conservative, and then the computation time was a little bit high. In other words, if we plot the area where Panther operates in a plot that represents the cost versus the replanning time, we can see that Panther operates in this area. Now, if we include more decision variables and more different initial guesses, we can move from this area of the plot to this other area, where we have been able to decrease the cost, but at the expense of computation time. So then the question is whether or not it's possible to achieve a cost very similar to Panther Star, which is the second algorithm, but with much less computation time. And this is something that we call Deep-PANTHER. The proposed solution is based on imitation learning, where Panther Star will be the expert, and then Deep-PANTHER, which will be a neural network, will be the student. And this is something that we train using the Dagger algorithm. Now, one key aspect here is how we capture the multimodality of the expert. The idea is that depending on the state of the UAV and the obstacle, we may obtain many different locally optimal solutions from the expert. For example, this is just one mode from the expert, but here we get 2 modes, 3 modes, and so on. And the question is how to capture this multimodality with a neural network whose output has fixed size. The way we propose to do this is as follows. We take the observation, we pass it through the student, which is this neural network, to obtain the student trajectories, and then we pass it through the expert to obtain the expert trajectories. With these trajectories, we compute the cost matrices, both in time space and in position space, and then we obtain this assignment matrix that assigns the student trajectories with the expert trajectories. This assignment matrix is then used in the loss to penalize the distance between the assigned expert and student trajectories. Now the question is how to do this, how to go from the cost matrices to the assignment matrix. There are many ways to do this. A popular way to do this is called the winner-takes-all approach, which has these 2 variations, but these approaches, they run either into equilibrium issues or mode collapse issues. Instead, we propose to use this different approach where we assign to each expert trajectory a different student trajectory while minimizing the assignment cost. This allows us to obtain the position trajectory, but then to obtain the trajectory, we use a closed form solution that maximizes the presence of an obstacle in the field of view given this position trajectory. If we look now at the results, this is for a static environment where here on the left you have the demonstrations collected from the expert, and here on the right you have the testing environment. In all the cases, we are able to generate at least one collision-free trajectory, and then our approach, Deep-PANTHER, is able to generate trajectories that are actually closer to the ones from the expert. And now, if we look back at the plot that we had before, where here we had Panther, and in this area we had Panther Star, the good news is that now Deep-PANTHER is able to operate in this area, where we have been able to decrease the cost compared to Panther, while achieving a replanning time 1 or 2 orders of magnitude smaller than Panther or Panther Star. These are the results for a dynamic environment, where again, here on the left, you have the demonstrations from the expert, and on the right, the testing environment. Now, one natural question is how well this generalizes. And to do that, we train a network using an environment where the obstacle follows a trefoil, not trajectory, but then we test that network in environments where the obstacle is following different trajectories. The good news is that in all the cases, Deep-PANTHER is able to generate at least one safe trajectory in all the replanning steps. And with this, I would like to thank you so much for your attention, and now I am happy to take any questions. Thank you.